All right, so 6.4, part 2. And I can't remember which of the Bernoullis this was named after. There were two Bernoullis, Jacob and, was it Nikolai? Was it? I don't remember I don't remember which of the two Bernoullis it was. Both of them did a lot of stuff. All right, so yesterday we came up with a method using an integrating factor to solve linear first-order differential equations. Well, Bernoulli differential equations are a special type of non-linear. And I'm just going to write differential equation. And what we do is we make a substitution to transform it. And I'm going to say a clever substitution. The BC book that we used for a long time would, in the homework, it would say, it would give you a hint on the homework problems. It would say, "Be clever," and the students really didn't like it. And then sometimes when you get an answer, when you work a problem, it would say at the end, "Surprised." All right, so our Bernoulli differential equation. So our definition. We have y prime plus p of xy. So we start out like a linear first order differential equation equals q of x y to the n. This part, the y to the n, makes it nonlinear. And I'm going to say if n is greater than 0. Because if n is 0, then we just have a linear differential equation. Because we just have that. If n is 1, we can divide both sides by y, and it turns into a separable differential equation. We can get all the x's on one side and the y's on the other side, and integrate both sides. So we're going to be working with a case where n is greater than 1. If n is, you can still use the technique of n equals 1, but you don't have to. There's an easier way. All right. So it looks a lot like a linear differential equation. So what mathematicians figured out is we can make a substitution to turn it into a linear differential equation. So we want to make a substitution so we don't have this y to the n on the right-hand side. So our substitution is what we do is, and remember that we end up, when we solved our first order linear differential equation, we wanted this side turned into the derivative of a product. So we want our substitution to do the same thing. So we want to get rid of this y to the n, and we want the left-hand side to be the derivative of a product. So we're going to guess that somehow we're going to end up multiplying y by y to the minus n. But we're going to do one other little thing so that it takes care of our left-hand side as well. So we're good with our setup. All right, so we're going to let z, which is going to be our new variable, equals y to the 1 minus n. And then z prime is, take the derivative of this, 1 minus n, times y to the minus n, y prime. Well, there's our y to the minus n. That's going to get rid of that y to the n on the right-hand side. And we're going to multiply the entire equation by this quantity. So if I, just looking back at my equation, I'm going to multiply both sides of this equation, the Bernoulli differential equation, by this 1 minus n, y to the minus n. So when I do this, I get 1 minus n, y to the minus n, y prime, well that's z prime, plus 1 minus n p to the x, p of x, y, when I multiply y times y to the minus n, I get y to the 1 minus n. That's a nice quantity. That's just z. Equals 1 minus n q of x. Well, let's rewrite this now. Well, this quantity is z prime. This quantity is plus one minus n p of x z. 1 minus n is just a constant, just a number. And that equals 1 minus n q of x. 1 minus n is just a constant. This is a first order linear differential equation. So we make this substitution. Z is y to the 1 minus n. This is z prime. Multiply by this quantity, and we transform that into a first order linear differential equation. And now we can come up with an integrating factor for this equation and solve for z. And then when we're done, we back substitute from our original change of variables to get y. So integrating factor is u of x equals e to the, sorry, got to get e in there first, e to the integral of 1 minus n, that's just a number, p of x dx. We just multiply p of x by that constant to get our new p of x. And our solution for z, if we plug into our formula, I always do it as the derivative of a product, but if we plug into our formula, the solution is z equals 1 over u of x integral 1 minus n q of x, u of x just like we had yesterday, and I'm going to explicitly include here in parentheses our plus c. So we remember that we have our constant of integration there. And the plus c is not in the integral. I'm just explicitly accounting for the constant of integration because it's multiplied by that 1 over u of x. And then we substitute we solve for y using z equals y to the 1 minus n. And we have the solution to our nonlinear differential equation. So we have these preliminary steps to get our linear differential equation, and then we solve this linear differential equation using our method from yesterday, and then we back substitute to solve for y. All right.
And this is on the quiz?
This is not on the quiz. And on the test for this equation, I would there are some problems in the homework that just say solve the differential equation, and they don't tell you what kind. On the test, I would say solve the first order linear differential equation or solve the Bernoulli differential equation, so you know, you'll know which technique to use.
So you put the y to the n, 1 minus n parentheses goes, and then you have to
Take the 1 minus nth root of that. Yeah, so it's going to be like the third root or the...
So you could just write this as y equals the n
Right,
minus
right, right,
root
right.
of that.
Mm-hmm.
Okay.
Mm-hmm. And we'll do an example here in just a
Oh,
second.
excellent.
All right, so questions on our method. All right. Let's take a look at an example.
Oh, good.
So we want to solve y prime plus 2x to the minus 1y equals x to the 6th y to the 3rd. All right, so this term, this y to the 3rd, makes it nonlinear. Because for a linear differential equation, the derivative and the function and its derivatives only appear to the first power. So that we get that y to the 3rd, the function is raised to the 3rd power. All right, so this is a Bernoulli differential equation. Because it has this similar form to a linear differential equation with n equals 3. So that's y to the n equals 3. So we're going to let z, we're going to substitute, equals y to the 1 minus 3 or y to the minus 2. Z prime equals, we'll take the derivative of this, minus 2y to the minus 3. This is part of the reason we do this, because we end up with a minus 3 there. We want to get rid of that y to the 3rd. Minus 2, y to the minus 3, y prime. Because y is a function of x. All right, and we're going to multiply our equation by this quantity, minus 2, y to the minus 3. So I'm going to multiply this original equation by minus 2, y to the minus 3. So I get minus 2, y to the minus 3, y prime, minus, when I multiply this, minus 4, x to the minus 1, y to the minus 2. Well, there's my y to the minus 2, there's my z. And that equals, we get rid of this y to the 3rd, I get minus 2x to the 6th. So for this equation, I would say p of x, this is a linear differential equation. Let me use a subscript here, or right below here. This is z prime minus 4x to the minus 1 z equals minus 2x to the 6th. This is a first order linear differential equation. P of x is minus 4x to the minus 1, and q of x is minus 2x to the 6th. And I'm just going to put a note over here. That's first order linear. All right, so now we can find our integration factor. Yeah.
Where do you get the negative 2x to the 6th?
Because I multiplied this quantity by minus 2 y to the minus 3. So we multiply everything, we multiply the entire equation by that quantity. All right, so now we can find our integrating factor for this equation. So u of x, our integrating factor is e to the integral of minus 4x to the minus 1 dx, which is, when I integrate this, e to the minus 4 natural log absolute value of x, which is e to the natural log of absolute value of x to the minus 4. And just like we talked about yesterday, we can drop that absolute value because we're multiplying both sides of the equation either by a positive quantity or negative quantity. So it doesn't matter. The sign doesn't matter. And I'm going to say x to the minus 4. Drop the absolute value. All right, so now our new equation. In our new equation, I'm going to multiply this first order linear differential equation by u of x. So why don't I'm going to put a star here. So I'm going to say multiply star by x to the minus 4, my u of x. Just like we did yesterday when we were solving first order linear differential equations. So when I do that, I get x to the minus 4 z prime minus 4x to the minus 5 z equals minus 2x squared. And now I recognize this quantity as a derivative of a product. So what's my product here? This is the first times the derivative of the second. So it's going to be x to the minus 4 z prime equals minus 2x squared. So if I take the derivative of this, I get this. Now we can integrate both sides. So I get x to the minus 4z equals the integral of minus 2x squared dx. Easy integral to evaluate. So x to the minus 4z equals minus 2/3 x to the third plus c. And z then, I'm going to multiply by x to the fourth. Minus 2/3 x to the seventh plus c x to the fourth. Yeah.
Where did you get that x to the negative 4 times z prime equals negative 2x squared?
So this was the way that we solved our first order linear differential equations without using the formula. So I just recognize that this is a derivative of a product. Okay. So yeah, the Bernoulli equation adds kind of an entire layer of extra steps. But now we're just doing exactly what we did yesterday. Okay? All right. And then we said now we have z, but z is y to the minus 2. So y to the minus 2 equals minus 2/3 x to the seventh plus c x to the fourth. So, not quite. Y squared is 1 over this quantity. So y is the square root of 1 over minus 2/3 x to the seventh plus c x to the fourth. Nonlinear differential equations tend to have kind of complicated solutions. Now imagine with this quantity, now we're done. That the Bernoulli, there's several steps of the Bernoulli equation adds an extra layer to these problems. Imagine if the problem then asks you to verify that this is a solution to this. So it's saying the derivative plus 2x to the minus 1 times this original function equals x to the 6th times this function cubed. That would take a lot of work to verify. That's a pretty messy equation. Make sure it works for one pair of values.
Yeah.
It's fine.
Right.
If it works for one pair of values, it
Probably
works for all the others.
You,
Not a good thing to say. Oh wait, no.
yeah, 1, infinity. What's the difference?
It is all the same.
It's they're close.
I know, Bernoulli.
And you will find that Bernoulli differential equations, their solutions often look something like this because z is some kind of power of y.
So we're almost always going to have a
Some kind of radical in there, yeah.
So, right. And then if it's negative, you just put the whole original quantity.
Right. All right, questions? A hint on your homework. There are some mixture problems on the homework, so that you have tanks and you have a solution and there's stuff going in and stuff going out. On those, so on the mixture problems, use the equation. So they develop an equation for a general equation for these mixture problems. Use the equation developed in number 35. So in number 35, they'll say, given these conditions, the equation, the differential equation that this mixture satisfies is such and such. So it'll give you the quantities and concentrations and this and that. Use the equation that they give you in number 35. Don't come up with it on your own. There's an example in the book, example number 5 on page 427. And number 47, it asks you to generate a slope field. I think you can search if your calculator doesn't do it. I know the 89 will do slope fields. I think you can search online, and Wolfram Alpha might generate a slope field. So you can look online for a way to generate a slope field from the differential equation. So for the mixture problems, you're just going to plug in the quantities that they give you into the equation in problem number 35. They give you an equation in problem number 35, and then you solve those differential equations. Mixture problems, I think the mixture problems are all separable. So you don't have to use first order linear, you don't have to use Bernoulli equations, you just get all the x's on one side, all the y's on the other side, and integrate. Okay.
So what about these ones that it's special? You said these are a special group of nonlinear. What makes it not one of these? This one has to be in the form.
It has to be in exactly in that form that we wrote. Right, for this substitution to work. Other nonlinear equations, you have to use other types of methods. And that's the kind of interesting thing about differential equations.